In this video, we're going to look at how heat is involved in combustion reactions and other reactions. A burning candle is an example of a combustion reaction. Many people believe that hydrogen is the fuel of the 21st century. Stop the video and answer these questions. And the answers are, we looked at this reaction in the previous video and found that this reaction released 285 kilojoules per mole of water. In a combustion reaction, a fuel reacts with oxygen in an exothermic reaction. Water is produced in this reaction, and if the fuel has carbon in it, CO2 is also produced. Natural gas is the fuel used in your gas stove at home and is also used in Bunsen burners. Stop the video and answer these questions. And the answers are, for the flame color, turning the Bunsen burner barrel adjusts the amount of oxygen that flows through those holes. Adjusting the valve at the bottom adjusts the flow rate of the methane gas. Let's say you're using a Bunsen burner to heat up water. We could predict how much fuel to use to heat up a certain amount of water to a certain temperature. Here are the equations we could use. So stop the video and take a picture of these equations so you'll have it ready later. Let's burn ethanol as our fuel. So stop the video and answer this question. To get the answer, first balance the chemical equation for the combustion of ethanol. Next, look up the delta H formation of each reactant and product. Then calculate delta H reaction by using Hess's law. This number tells us that when 1 mole of ethanol burns, 1230 kilojoules of energy is released. For 1 gram of ethanol, do this conversion. You just calculate how much heat is released when 1 gram of alcohol burns. Let's use that heat to heat up water. Stop the video and do question A. To get the answer, start with this equation. The heat gained by water is the physical heat transfer, so that's equal to m times s times delta T. The heat lost by the ethanol combustion reaction is the chemical heat transfer, so that heat equals delta H. We know the specific heat of water, T final, T initial, and delta H for the combustion reaction. So let's solve for the mass of water. And that's equal to, then use density to convert from grams to mils. Stop the video again and do part B. And the answer is, to get that mass, use this equation. Now we know the mass of water, but not the mass of ethanol. The ethanol combustion reaction releases minus 26.8 kilojoules per gram, so this is how we can set up the right side of the equation. Whew, it's so hot, water will boil. Stop the video and answer these questions. And the answers are, apply Hess's law. And for the reverse reaction, check out what happened at McDonald's. Is it worse to be burned by steam or hot water? Stop the video and answer these two questions. And the answers are, for part B, look at boiling water from room temperature as a two-step process. So Q total equals a lot more energy is required to boil water. Stop the video again and do part C. To get the answer, compare these two. A lot more heat is lost by the steam due to the gas to liquid phase change compared to the heat lost by the hot water. When an ionic compound dissolves in water, heat is either absorbed or released depending on the ionic compound. So stop the video for a minute and think about the information you need to know to determine whether NaCl can be used in a hot pack or cold pack. Okay, here's what you need to know. Based on the NaCl dissolution reaction, you can calculate delta H of that reaction using Hess's law. Delta H is positive, which means heat is gained by the chemical reaction and heat is lost by the water surrounding the reaction. When water loses heat, the temperature drops, so NaCl can be used in a cold pack. Then use the heat equation to figure out how much salt is needed to cool down 50 mils of water from 25 degrees to 0 degrees, which are the design specifications for a cold pack, and then check to see whether that mass of salt is soluble in 50 mils of water. It turns out that 20 grams of salt is soluble in 50 mils of water, so that mass of salt can't be used to make a cold pack. So you're going to determine whether each salt can be used in a hot pack or cold pack based on delta H. Then you'll choose 2 salts to test for a hot pack and 2 for a cold pack based on cost and safety. Then you'll test the performance of each salt. Finally, you'll choose 1 salt for the hot pack and 1 for the cold pack based on cost, safety, and performance. I'm pretty sure all of us have been in a car, so let's see how a heat engine works. Stop the video and answer these questions. And the answers are, gasoline is a liquid of which octane is the main component. This combustion reaction produces gas products. We want the gas to expand so it pushes on the piston to produce work. In the heat engine schematic diagram, the combustion reaction occurs in the hot reservoir. Heat is converted to work when the gases expand and push against the piston. Not all of the heat is converted to work because gas molecules move in random directions. In other words, not all the gas molecules push against the piston. And the efficiency of an internal combustion engine is only around 20%. Here are 3 fuels that are used in internal combustion engines. So stop the video and practice these calculations. And the answers are, on a per mole basis, octane, the biggest fuel, produces the most energy. But on a per gram basis, methane produces the most energy. Earlier we said that heat engines produce work from the heat released in a combustion reaction. Work is defined as the ability to move matter. In physics, work is the force exerted through a distance. Let's divide force by area, that gives us pressure, and let's multiply distance times area, that gives us volume. In chemistry, we will use this definition for work. Unlike solids and liquids, gases can compress and expand. So work involves gases. When a gas expands, V final is greater than V initial, so delta V is greater than 0, which means work is less than 0. When work is negative, work is produced. In other words, work is done by the gas on its surroundings. On the other hand, when a gas contracts, V final is less than V initial, so delta V is less than 0. That makes work greater than 0. When work is positive, that means work is supplied. In other words, work is done on the gas by its surroundings. Now, we can calculate whether work is produced or supplied in a chemical reaction. Let's take a look at the butane combustion reaction. First, write a balanced chemical equation. Next, compare the moles of gas reactants to gas products. There are more moles of gas products. Now, the ideal gas law tells us N is directly proportional to V. So if delta N is greater than 0, that means delta V is also greater than 0. Therefore, work is less than 0, which means work is produced. If delta N is less than 0, stop the video and fill in those blanks. And the answers are, so the butane combustion reaction produces work because there's more moles of gas products than reactants, and that causes the gas to expand.